The last crypto challenge was SMarT2. It says, I'm sure you'll never guess what comes next, now do it without the key. So this is an extension on SMarT1. We're given a new output file. Let's generate here. And so last time we had mask, key, and then some pairs and the ciphertext. This time we don't get the key. I did not solve this challenge during the CTF, as you can see. So I referred to write-ups afterwards to help me. The challenge author did a write-up, which you can see here. I think, again, I didn't see the hint here that we were supposed to be using an SMT, and same as the first one, I didn't think that you could use SMT solvers on S boxes, but once you know that you're supposed to use an SMT solver, and if you know how to use an SMT solver, this challenge really isn't too bad. So once I saw it was an SMT, there's one thing that's very neat that I really like that the challenge author did in their solution. It's this right here, a nifty little trick which I'll be talking about, but the rest of it is just very standard Z3. Yeah. Anyways, let's look at the solution. Oh, this is the challenge file. It's the same algorithm as last time. Was that the challenge file? No, this is the challenge file. This was my solution. Basically, we don't know what key is, so this is just Z3 stuff. We're gonna generate a bit vector of all 12 bytes of the key, and each is just a byte long. You use bit vets instead of ints because at some point we do an XOR operation, and I think also shift operations. You can't use it on ints. You need to use it on bit vecs. Then we generate the mask. The mask is given to us. I think to keep Z3 happy, it's just best to convert everything to bit vec vals. There's this S box thing, same as last time. There's the transpose box, same as last time. We're going to change this rotate right thing. Z3, I think by default the shift operator, there's like a logical one, and there's a name for the other one, I forget. But I think on Z3, like if you rotate if we were to rotate this to the right by 1, it would return 1110, whereas by default Python would do 0, 1, 1, 0. So Python just shifts everything to the right by 1, and it'll just delete this value, whereas Z3 by default will take the 1 and bring it back to the other side. And we want the Python way, and to do that, you just do this left shift, or logical shift right. We replace, by default, there's an XOR function using pwn tools. We replace it with this one. I think pwn tools does some mapping that Z3 didn't like, so I found it easier just to write our own. So this is the encrypt function. We cleaned some stuff up. I think by default the encrypt function like wraps things in byte objects, byte arrays. Since we're doing everything in Z3, we don't actually care about any of that stuff. So this sub F thing, like I said, I thought that S boxes were very difficult for Z3 to handle, but it turns out there's a very, I guess, clever way to get around this that I got from the challenge author's write-up, is you can actually define a function in Z3, and basically we're just telling Z3, like, don't worry about the S box. The S box is actually just a function, and we just tell the solver how this S box function works. Even though it's just a map, a lookup map, we're just going to call it a function and tell Z3 how it works, which is, I don't know, that's great. I didn't know this. This is a clever little trick. I like it. So I copied this code, word for word, I think, somewhere. Yep, right here, init S box, and here's the S box function. So super useful. So that's how we do the S box lookups. Then we have the standard rotate right. We're generating a temp variable for doing the transpose. We can see the transpose, again, we have to do a left shift or logical shift right here instead of the operation that was being done. Then we do an XOR. Again, we haven't really changed much of the code. Like as once you know this is an SMT challenge, it's really not too bad. We're just making, basically the way that I think you actually solve this challenge is you just wrap the input and output into Z3 objects, and then Z3 will complain when it doesn't like something, and then you just fix that thing, and you just run it a couple times. I think there's like 4 things in the code you actually need to change, and once you've done all that, the answer just pops out. We have the ECB function. We're not going to do a length check because we already know that the key and everything is padded to what we want. This was some input that we don't care about. And cool, so we start the Z3 code. So we have S, this is our solver. Again, this is that S box function, that really cool code. So this will do the S box lookup for us. And basically what it's doing is just gonna add a bunch of rules to the solver for our function. So when we call this later, it knows what the output is. So like I said, we don't know for SBox or for SMarT2, we don't have the key. So the first thing, but they give us a bunch of plaintext and encrypted ciphertext. And so using this, we can actually reverse the key. So what we're going to do is for each of the pairs, we're just going to give it to Z3. So we take the input and we just convert it to Z3 bitvex. And we take the output, we also convert that to bitvex, and then we encrypt the function. So this is our Z3 object. This is a Z3 object. This is a Z3 object, or Z3 unknown object. You know, it's a bunch of like XORs and ANDs and, you know, all the math stuff. And then we add that to the solver. And when we're all done, we've added all the pairs. I mean, maybe we only need one. I don't know how many pairs we actually need, but we do that and we ask if it's able to solve itself. It is able to solve. It says SAT. Then we generate a model and we ask it for the key and it'll give us the key. And then from there, we could go back to the code we had in SMarT1, which did the manual decryption, but we already have the SAT solver set up. So basically I just generate the flag ciphertext, put that into bitvex vals, the flag plaintext, which is our actual Z3 unknown object. Then the key, we convert that back into a Z3 bitvex value, and we start a new solver. We give it that SBox function. Maybe we could have used the old one, I'm not sure. I just like to keep it clean, so we just generate a new solver. And then I print some values out, and then we just do the actual encryption. And then when we're all done, we just say, hey, Z3, match the input to the output. We do a check, it'll say SAT, and then from there we just take out, byte by byte, we take out the flag. It takes a second to run. What did I call this? Child 2. I mean, barely a second. And that was it. Like I said, really not too bad of a challenge once you know you're supposed to be using an SMT. It says if you didn't use an SMT solver, that's cool too. I think the challenge author and some other people used a byte by byte relationship. There's also a more structured attack on the cipher. Again, this is from Seraphin, the challenge author. The fact the cipher only performs 2 rounds. Since the last round is very weak with an XOR, substitution permutation of the blocks in the cipher, blah, blah, blah. This means that the actual encryption security depends on the first round and an XOR. So removing that implies that the permutation step in the first round is then again weak, since it just represents the permutation of a keys bits XOR of the ciphertext. This gives a relationship of this, which can be brute forced by byte by byte. And I think other people did this. I was reading some write-ups from someone called Maple. Here. Go to cryptography, SMarT2. Reading their write-up, I think that's also what they did. Yeah, they kind of talk about it here, which is pretty cool. Byte by byte brute force. So different ways to solve it, but I think for this one, thankfully Z3 worked, and it, as you saw, it just pops out in a second. So probably the easiest way to do it. Anyways, thanks. That's all the crypto.